Okay, well, thanks again for having me. It's a great pleasure after a number of virtual conferences to be really here. I'll be talking about a paper that appeared a few months ago with Marine de Clercq, colleague Evelyn, Philippe Hager, and Maxime Pavlov. And I will give you one slide about black holes, and the rest will be about complexity. So this is just some motivation. So complexity, as I'm sure you've realized, is increasingly appearing in various discussions of black hole. I'll give a few motivations. It's been proposed to compute the volume behind horizons of black holes and related quantities. It's also related to the difficulty of reconstructing a black hole interior. It's been proposed that it actually plays an important role in protecting causality. Now, I realize that for people working on horizonless microstates geometries, this might not be the most convincing motivations. So let me also add that complexity also plays a role in the difficulty of distinguishing various black hole microstates. Now, many of the discussions of complexity have been focusing on gravitationally dual quantities, which can be computed relatively straightforwardly. And we need tools which are being developed to actually compute complexity in quantum mechanics or more generally quantum field theory. So what is it that causes black holes to be complex? One idea is that it may be chaotic time evolution that takes simple states and develops them into very complex ones. And so one question one can ask to address quantitatively is whether complexity is able to distinguish between chaotic and integrable time evolution. And that will be the theme of this talk. So what I'll do is introduce a bound on a certain notion of complexity of time evolution. Then I will apply it to two classes of models. One is some classes of Syk models, integrable and chaotic versions. And then I'll apply them to what we believe are more generic models of integrable systems and also chaotic versions, namely so-called quantum resonant systems, which I'll introduce. And then I'll conclude. So one notion of complexity in theoretical computer science is circuit complexity, which is defined as the minimal number of simple operations or simple gates one needs to perform a certain quantum computation. There is a geometric version of complexity that was inspired by this. This was proposed by Nielsen, and it's defined as the length of the shortest path in the manifold of unitaries between the identity operator and the unitary operator of interest, which for us will be the time evolution operator at a certain moment t. So to compute lengths of such paths, one needs to endow this manifold of unitary operators with a metric. And a simple possibility, which will be too simple for our purposes, is to take the so-called Bi-Invariant Metric defined in this way. So to compute it, one introduces the velocity. So given a unitary u of t as a function of time, one computes a time derivative. This defines this velocity v. This velocity can be expanded in a basis of generators of Hermitian matrices. And I'm normalizing this basis as follows. And then the bi-invariant complexity is simply defined or simply reduces to this expression. So the integral over time of the trace of the velocity squared, the square root of this. And expressed in components, this is what you need to compute. So this would be bi-invariant complexity. Now, in practice, one wants to introduce a slightly more complicated complexity metric. And this is meant to encode the notion that some gates or some operations will be simple or local, and other operations will be more complicated, will be hard or non-local. And to do this, one splits the tangent space of the unitaries into easy and hard directions. And the easy directions I will consistently label by indices alpha, and the hard ones by indices alpha dot. And now I'm going to introduce a new metric on this space of unitaries, which weighs the hard directions by some cost factor mu, and the easy directions just 1. So if mu is equal to 1, I recover the bi-invariant metric and the bi-invariant complexity I had before. But typically, we will choose mu to be some large quantity of order the dimension of the Hilbert space. So this will be exponentially large in the number of qubits if you wish. So in this manifold of unitaries, you will preferentially look for the easy directions to go from the unit operator to the time evolution operator at time t. And we will always make our choice of easy versus hard in such a way that the Hamiltonian itself is always considered an easy direction. And okay, so this is the notion of complexity I'm going to use. And the goal will be to characterize the complexity of the time evolution operator for integrable versus chaotic models. And there's been previous papers that have attempted to do this using a different approach from ours.
Sorry, just to understand this. Anyway, all of these operators can be considered Hamiltonian in a sense. They are time derivative of evolution operator. It's these.
Yes, but these...
So you take a system and you believe you know the Hamiltonian of the system.
Yes, you take a physical system, it has a Hamiltonian. And so, for instance, in practice, we're going to define a locality degree, for instance, by the number of fermionic operators that appear in a term of the, well, the number of fermionic operators, for instance, could be one notion. And we will always put the cutoff between local and non-local ones in such a way that the Hamiltonian falls in the easy category.
But that's my point. I mean, you can consider the full object, which is complex in your sense, as a new Hamiltonian of a new system.
Yeah, but there will be one Hamiltonian that will be the physical Hamiltonian of the system, of which will define the time evolution operator and of which we want to compute the complexity. So maybe it will be more clear when there's some concrete examples, which will be there in a few minutes. Okay, so first let me discuss the version of complexity in the bi-invariant metric before we move on to introducing cost factors. So the geodesics in the bi-invariant metric turn out to have constant velocity v. So here are the geodesics. And we look for geodesics connecting the identity operator and the time evolution operator at some time t that we're interested in. So the geodesics take the following form, where h prime should be such that at time t, exponential minus I h prime t should be equal to the time evolution operator itself at time t. Now I'm going to assume that I don't have degeneracies in the energy spectrum. And in that case, this identity implies that the velocity of this geodesic is related to, well, takes the following form. So if the kn were 0, this would just be the Hamiltonian. But now I'm allowing myself to shift these energies by 2 pi integer divided by t, because then this is still satisfied. So this is the freedom I have. And what I need to do is choose this kn in such a way that the length of the geodesic is minimal. So here is the complexity, is the minimum of the sum of e prime n squared, the square root of all this. If I write it out, it takes this form. And this is actually a trivial problem to solve. It's an independent sum of squares, so you just have to choose each kn such that the shifted quantity here lies between minus pi and pi. So this is simply called rounding to the nearest integer. So this is extremely simple to compute. Unfortunately, it's a bit too simple. But let me first say what happens at early times and then what happens at later times. At early times, well, you can see that to minimize this, no shift is needed, because if this ENT is small enough, the Kn will be automatically 0 when you minimize this. So that means that the geodesic that determines the early time complexity is simply corresponds to the time evolution, exponential ITH. So that also means that the complexity at early times will just grow linearly in time with this coefficient that is determined by the energy spectrum. Now, I'll be interested in comparing the complexity between different Hamiltonians, so I need some sort of normalization to make this meaningful. And to do that, we will shift the energy such that the trace of the Hamiltonian vanishes. And I will rescale the Hamiltonian, I will rescale time if you wish, such that the trace of h squared is equal to 1. And in those conventions, the early time growth of this bi-invariant complexity is simply equal to C of t equals to t. And this actually continues to hold when we use the complexity metric. So with a non-trivial cost factor at early times, it will always be simple, and the question will be, how long does this early time linear growth last? I should make one comment on conventions, just not to confuse any experts. The normalization used by Nielsen and several other papers differs by our normalization by a factor of the square root of the dimension of the Hilbert space. So this, if you're an expert, it will be useful, otherwise don't worry about it. Okay, so for later times, it's also clear that choosing Kn equal to 0 will no longer be the minimum. So we can find shorter geodesics by choosing this non-zero Kn. And what one observes is that at late times, the quantity saturates after a period of linear growth. And there is a clear intuition for this. Namely, if you assume that a generic point, so not a very early point, but a generic point along the line En times t, if you assume that such a generic point is as close to the lattice as is a random point in the space, then you can look at the distribution of these distances of random points to the lattice, and there's a simple mathematical result that this distribution for large dimensions actually concentrates. It localizes on a value proportional to the square root of the dimension of the Hilbert space at large D. And actually, if you check numerically how the complexity behaves, and I will show it on the next slide, you see that the prediction you get from this simple assumption actually works very well, both for the height of the complexity plateau and for the variance around it. So what is the bad news? Well, the bad news is that the bi-invariant complexity plateau height does not distinguish integrable from chaotic systems. So it's too universal, actually. And that's why we will need to introduce cost factors and work with the complexity metric to get some more interesting results. And okay, a small comment. When I talk about the late time plateau, I don't mean the extremely late times where you get Poincare recurrences, but these for most systems will be unobservably late anyway. So here is what you get for the bi-invariant complexity. So this is the phase of universal linear growth, and then there is the saturation, and you can see for extremely late time, so here is a 10 to the 5th, that it still oscillates with a certain variance around the plateau value. And there's no very pronounced differences between chaotic and integrable. If you look In very detail, you might find some subtle differences, but to a first approximation, the complexity curves are just the same, and that's why we're not going to be interested in this bi-invariant complexity.
Is there anything significant about the oscillation frequency?
Well, so that's one of the differences between the two, and it might be interesting to study. I don't know. But we will get more dramatic differences when we introduce cost factors. Okay, so for mu larger than 1, things become, yes?
Do you see Poincare recurrence if you even go beyond this exponential of time?
Well, so the question is, do I see Poincare recurrences? Well, one expects them, definitely, but it would be way too late to simulate. So we don't see them in the numerics. Okay, so now we introduce the cost factors. In that case, the minimization will be far from trivial, as I will explain. But we can find rigorous upper bounds to the complexity. And then the question will be, how interesting are these upper bounds? You can sort of think about it as a variational principle in quantum mechanics. When you cannot actually compute ground state energies, you can do a variational principle and you find some value. It will not be a systematic approximation. You don't know how far away from the correct answer you are, but still it's useful to use these variational approaches in many branches of physics. And then you compare and see whether you get interesting results. So that will be the spirit. So in this case, minimizing over all possible curves, which would be the exact solution to the problem, is way too hard. So we will choose a specific infinite class of curves that we will minimize over. So that will clearly give an upper bound to the exact complexity. And the family of curves I'm going to choose is precisely the geodesics of the bi-invariant metric. So these will generically not be geodesics of the complexity metric with the cost factor, but that's fine. We're going to minimize over a restricted ansatz. It will give us an upper bound, and then we will need to check whether this upper bound is interesting. And for me, a criterion to decide on that is whether it successfully distinguishes integrable and chaotic evolution. So the next problem is that finding the bi-invariant geodesic with shortest length is also too hard a problem. And actually, I will reduce this problem to a problem that was the basis of lattice cryptography. So even this problem is so hard to solve exactly that people use it as a basis for cryptography. And it's kind of amusing that this quantity actually, as I will show, reduces to a well-studied problem in that field. So I sort of gave you the philosophy. The question will be, is this bound useful? And I will claim that it manages to separate chaotic from integrable time evolution. So let me give a few details. So here are the bi-invariant geodesics again. So constant velocities h prime. H prime has the same form as I showed you before. So I decompose the projectors on energy eigenstates into easy and hard directions. The expansion coefficients using the metric I gave you before take the following form. And using all this, you can write the norm squared of the velocity with the cost factor in this way. So if mu were equal to 1, you can show that this reduces to what we had before for the bi-invariant complexity. But of course, having mu much larger than 1, of order the dimension of the Hilbert space, will of course make a big difference. And in fact, it turns out to be convenient to rewrite this expression for the velocity squared as the length of these shifted energies we had before, but not with the trivial metric, but with a modified metric involving a matrix Q and M. And this matrix Q is defined in the following way. We just introduced it to be able to do this rewriting. So we sum over all the hard directions, and the quantity we sum is written here. So N and M are again the energy eigenstates. And one can show that it can be rewritten in terms of the local directions as follows. And given this, the bound on complexity that we're going to study is equal to this. And again, when the cost factor mu were equal to 1, this would drop out and we would reduce to the bi-invariant complexity we had before, which was trivial to compute. But this is a much harder problem. So let me give you some properties of this matrix Q because it will play an important role later. So the eigenvalues of Q are between 0 and 1. You can easily see that they are larger than 0 via this argument because this is clearly positive. And running a similar argument using the second way of writing Q, it's also clear that the eigenvalues will be below 1. And another thing to notice is that the vector that consists of the energy spectrum of the Hamiltonian is a zero mode of this matrix Q. The argument is quite simple. This can be written as this expression, which involves a trace of some non-local generator with a Hamiltonian. But because I was assuming that the Hamiltonian is always a local operator, it will have no component along the hard directions, and so this thing vanishes. So there will be always one zero mode of the operator Q, and actually you can show that any zero mode of this matrix Q will correspond to a purely local conservation law of the system. And you can actually imagine that if you have a zero mode of this matrix Q, that will be a direction along which you can reduce the complexity without being penalized by this large penalty factor. So that's why the zero modes of Q, or more generally small eigenvalues of Q, will be very important when you try to reduce the complexity. Okay, so now we know which problem we have to solve to compute our bound on complexity. We have the minimization problem on some hypercubic lattice, but on a space with a non-trivial metric. So we take the point E and T, which is somewhere in the space in which the lattice lives, and we're going to ask what is the closest lattice point to this point. And the difficulty is that we're not using a trivial Euclidean metric. And so this problem is equivalent to solving a lattice problem in flat space, but with a non-standard basis, which is not hypercubical. So you can easily go from one to the other. In the literature on this problem, people usually work in flat space, but with a non-hypercubic lattice. And so this problem has a name. It's called the closest factor problem, and it's very difficult to solve exactly. All the known algorithms run in time exponential in D, and so D was the dimension of the Hilbert space, so it's itself exponential in the number of qubits, if you wish. And so that's why it's the basis of lattice cryptography. But it turns out that you can find approximate solutions in polynomial time. Now, when you do cryptography, an approximate solution will not help you. But if you want to compute this complexity bound, you can be hopeful that if you have an approximate solution, it will already tell you something, and that's what we will exploit here. So first, let me give you a very simple slide just to illustrate the fact that a simple rounding method that we used for the bi-invariant metric will not work if you have a non-hypercubic lattice or basis. So suppose that this vector E is the vector of which I want to find the closest lattice point. So of course you can easily see with your eyes which will be the closest lattice point. But the problem is that I'm going to give you a basis that defines the lattice, which is skewed. So here is my first basis vector, B1, and here is my second basis vector, B2. So let me expand the vector E I'm interested in into this basis. So it's 0.6 times B2, and then I have to subtract 6 times B1 to land on this point. So now if I did the naive rounding which solved the problem for me with the Bi-Invariant metric, it's clear what would happen. I would just round this 0.6 to 1, but it's also clear where that would take me on the lattice. It would take me to this rounded value, which is obviously not the closest lattice point to this one. So this is just a simple illustration that the simple method that solved the Bi-Invariant complexity is not going to be of much use here. So one needs more sophisticated algorithms. Unfortunately for us, those have been developed by others. So we use a succession of 3 algorithms. The first is the LLL algorithm after the authors listed here. And what that does, roughly speaking, is it takes some basis of the lattice and it converts this basis into some rounder one, where the basis vectors are more orthogonal to each other than the original ones. So that's called the basis reduction. So first you do that, then you use the nearest plane algorithm by Babai. And roughly speaking, what that does is it takes some hyperplane of the lattice and it takes a family of parallel hyperplanes and it looks for the closest one to the point you're interested in. Nothing guarantees that the closest lattice point will be on that plane, but still it will give an approximate solution. You project it orthogonally on that lattice plane, and then you start again in one dimension less until you have a single lattice point. And then you can improve the algorithm a bit more by running a greedy algorithm on the result. And what the greedy algorithm does, it takes the solution that you had from the previous algorithms, and then it checks in each of the d directions of your space whether if you move in that direction, you can find a better solution. And after you've checked all that, you move in the direction of biggest gain. So those are 3 algorithms that we run successively. We've tried also subsets of that, and I will give you some results about that. And all these algorithms, importantly, run in a time that is polynomial in the dimension of the Hilbert space. And okay, just in computer science, roughly speaking, whenever something runs in exponential time, it's considered way too hard to do in practice. Whenever something runs in polynomial time, it's considered feasible. So when it runs in polynomial time, you're happy. So, okay, so that's the method. Now I'm going to apply it. And first I will apply it to Syk models. Those were studied before in Vijay Balasubramanian's group using other methods. So this will be nice as a benchmark. Let me introduce the models of interest. So you take some collection of n fermions, and I'm going to use them to make 3 different Hamiltonians. The first is what we'll call the free Syk model. So you take some arbitrary matrix Jij, and you have some quadratic Hamiltonian. And then by combining these size into operators J, I will not give you the details here, you can write them like this. This J is obviously something quadratic in fermionic operators, and the J's have eigenvalues plus or minus 1, so it's easy to read off the energy spectrum from this expression. So you sort of block diagonalize this Hamiltonian. So that's a free model, it will be very simple. Then I will modify it into a slightly more complicated model which is still integrable. And this we simply do in this language with the matrices J3. We simply do by adding to this free Hamiltonian some quartic one. So there's 2 J's and each J is quadratic in the size with some arbitrary matrix, some arbitrary lower diagonal matrix M. The details don't matter too much. And you can easily see that this is still an integrable model. And then we will also want some chaotic Syk models, and this is probably the version of Syk that you might be most familiar with. You take some quartic term here, where these J's are just random matrices from a certain distribution. So I need to introduce some notion of locality if I want to discuss complexity here. So I define the local operators. Well, I choose some locality degree k, and then any operator with less than k fermions I consider local, and anything that cannot be written as a product of less than k fermions I consider a non-local direction. So to come back to Massimo's question from the beginning, so for instance, if I have some quartic Hamiltonian, some product of 6 fermions that cannot be reduced to at most 4, I would consider a non-local direction for that system. Okay, so for free and integrable SYK, there were results on the complexity by the Penn group, and they used model-specific methods to reduce the complexity. So their methods crucially depended on the specific form of the Hamiltonian, and in particular, they relied on many quadratic and quartic conservation laws that these systems have. And those conservation laws, they correspond to many zero modes of this matrix Q that I introduced. And remember, every zero mode of Q gave you possibilities to reduce the complexity. So there's many of those here. Since they are like quite local, it's easy to use many of them. And they got indeed a dramatic reduction of complexity by using them. So
you can have non-local Hamiltonian that are still integrable in a sense. Suppose that I take the square of my Hamiltonian or the 27th power of my Hamiltonian, that's integrable as well.
Well, yeah, so you can have integrable Hamiltonians that involve more higher powers of fermionic operators or more fermionic operators if you wish.
That you would call non-local, however.
No, then if I was interested in the complexity of time evolution for your Hamiltonian, then I would introduce a notion of locality, a choice of k, where k is large enough such that the Hamiltonian that you're interested in is local. Mm-hmm. So if your Hamiltonian involves 8 fermion terms,
sinh of h, the exponential of h, or
yeah, okay,
the logarithm of h plus 1.
Yeah, if it's not polynomial, then I would have to think about it. That I don't know. So let's restrict for simplicity to polynomial ones for now.
Okay, thanks.
Okay, so for these systems, we just ran our automated methods, so these algorithms that we got from the literature, and we essentially recovered the results for the free SYK model. Then we significantly improved those for integrable SYK, and we also understood why. There were some additional linear combinations of conservation laws that could be used to reduce it further, which had not been used in the previous work. And then also we were able to run our algorithms also for chaotic SYK, for which there were no prior results on the plateau height. And so here are some plots I will show you. So first for the free SYK. So this lowest line is the one that appeared in previous work using model-specific methods. Then if we use this LLL basis reduction mechanism and the Babai nearest plane algorithm, we would have this dashed line. So it agrees with the proposed exact result most of the time, but at some places it overshoots. And if we add the greedy algorithm, we improve at many places, and most of the time we're spot on. At some places we're a little bit above. But we didn't use any of the specific input of this model. So this is just some sanity test of the algorithm we have. It works pretty well here. Then for the chaotic SYK, and you can actually compare the values on the vertical axis, you see that the linear growth lasts much longer, and then it plateaus at a much higher value than for the free SYK. So here we didn't have anything to compare against. And then for the integrable non-free SYK, this was the result in previous literature, and this is what our algorithm gave on the nose. And as I said before, we can explain why there is this difference.
What value of n are you using?
Yeah, so these are Hilbert space dimensions, I think, of order 10 to the 4th. So here are values of n, if you wish. Yeah, so 2 to the n divided by 2. So I think it's sort of what I said. Okay, so here is the plateau height as a function of n. So n is the number of fermions. You see for the free and the integrable version, you get these lines, and then for the chaotic one, you have twice the slope. If you divide out the square root of dimension of the Hilbert space, you get the convention of Nielsen for the complexity. And then you see that for the integrable versions and the free version, it becomes, you lose the exponential dependence and it becomes power law. Note that this is logarithmic scale and this is not logarithms. And so this is power law complexity for integrable models. For the chaotic ones, it would be a d divided by square root of d, so it would still have exponential behavior in the number of fermions. Okay, so these are results for SYK, but SYK, at least the integrable SYK, is quite special in several ways. It's not a generic integrable system in the sense that there are unusually many quadratic and quartic conservation laws, and these very local conservation laws play a huge role in the complexity reduction that we had. And furthermore, these conserved quantities that we have, they all have the property that the spectrum of eigenvalues is integer, which is also a bit unusual. So you might worry, is this really a good model for a generic integrable system? A second reason for wanting to go beyond fermionic models in general is that fermionic models don't tend to have a conventional semi-classical limit. If you really and if you are really interested in chaos theory, the most solid definitions of chaos refer to semi-classical limits of quantum systems. So this motivated us to study complexity in a different class of systems, which I will now introduce and which we claim is more generic. And these are the quantum resonance systems. So what are they? They're given by this simple Hamiltonian. So you have some bosonic creation annihilation operators labeled by some index m or n, which runs from 0 to infinity. So there's an infinite number of bosons. And you have some quartic Hamiltonian, 2 annihilation operators, 2 creation operators, and then there's some interaction coefficients C, and the choice of these interaction coefficients picks the model, basically.
Don't you generate quadratic terms when you come to groups and stuff? I mean, this Hamiltonian is very fine-tuned because you're getting fourth order.
Well, it's just a quantum mechanical system, right? I don't have to renormalize anything. This is just a quantum mechanical Hamiltonian. No, I think I can just study it in itself. And,
okay.
And it appears very natural in many systems. I may be able to say a little bit about that later. So actually, I can say the classical version of this Hamiltonian appears if you do weakly nonlinear perturbation theory. So actually, we first ran into this kind of Hamiltonians when studying the ADS instability problem, where you have some fast oscillations and then you have some slow modulations above that. And if you're interested in the slow modulations, you sort of average out over the fast oscillations to zoom on in the slow dynamics. And that is typically given by these quartic Hamiltonians. And they come from a quadratic Hamiltonian with a small perturbation by sort of going to the interaction picture. And going to the interaction picture kills the quadratic part, and that zooms in on the quartic one. So this actually describes the weak nonlinearities in the system, if you wish.
Okay, thanks.
Yeah, so they do appear very naturally in many physical settings. ADS instability, Bose-Einstein condensates, there's many settings where they appear. So you generate a Hilbert space using these creation operators in a standard way. And if you look at this Hamiltonian, there's 2 obvious conserved charges. One is the particle number, because you annihilate 2 particles, you create 2. So n is conserved. But also m is conserved. And this is like some sort of linear energy, if you want. Because this Hamiltonian is resonant in the sense that n plus m is always equal to k plus l. This comes from the resonant approximation that zooms in on the nonlinearities that play an important role at long time scales, the ones that don't get averaged out, but that can have effects that build up in a long time scale. So those are the relevant ones. And you can see from this condition, it straightforwardly follows that M is also conserved. So now we have an interesting situation. We have an infinite dimensional Hilbert space. But so usually you would think, okay, this is very hard. We cannot diagonalize infinite dimensional matrices. But the Hamiltonian is block diagonal using these conserved charges N and M. And each block is finite dimensional. So now you can just take the Hamiltonian block by block. You order them from small to large. And you start diagonalizing for as long as you have energy for, or as long as your computer is willing to do it. And by going to higher and higher blocks, you can imagine to get closer to classical limits of the system. And so each block consists of those states with specific values of N and M. So as I mentioned to Josif before, these classical versions of resonance systems appear as controlled approximations to weakly nonlinear dynamics. Depending on the choice of interaction coefficient C, there's a huge variety of dynamical behavior that you can get. You can get turbulence that has been studied by PDE mathematicians. You can have recurrences, you can have integrability, you can have invariant submanifolds where you have integrable dynamics even though the whole system is not integrable. You can have chaos, strong chaos. There's a wide spectrum of dynamical behaviors that are possible. So that's why we were very curious to see how this complexity would behave across this spectrum of possibilities. So let me give one example of a rather generic-looking integrable model. If you choose these interaction coefficients to be 0 if all the indices are non-zero, and 1 if at least one index is 0, it's called the truncated Sago model for reasons I won't go into. And this turns out to be an integral model in the sense of lacks integrability. And if you draw the interaction coefficient C from some normal distribution in a random way, you will get a chaotic model. And just to convince you of that, we plotted a level spacing statistics as follows. And you see for this random model, you get a nice Wigner-Dyson distribution. And for this truncated Sago, it's spot on the Poisson distribution. So I need to introduce the notion of locality here. So this Hamiltonian changes at most 2 modes in a given state in a certain block. And so here, by convention, I'm going to say that this Hamiltonian has locality degree 2. You could have 6th order Hamiltonians, 8th order Hamiltonians that would have higher locality degrees. So I think there's an obvious way of defining locality here. And I will show you results later, but let me first summarize them. For this truncated Sago, which we believe is a more generic integral model than integral SYK, we see a complexity reduction compared to chaotic versions, but it is much less drastic than for the integrable SYK that we had before. So there is a noticeable difference in plateau height between integrable and chaotic, but it's of order 10 to 20%. It's not this dramatic reduction from exponential to polynomial. And we can discuss later what the implications might be. So here are some plots. So on the left side, this is the initial linear growth, and this is the plateau. This is for locality degree 2, so where and this is for higher locality degree 6, where more of the operators are considered local. And clearly, when you have more local operators, you will reduce the complexity more than if you have less of them. And you see that if you increase the locality degree, there's a bigger separation between chaotic and, for instance, the truncated Sago model in red that we have here, but they are clearly distinguished. Already here, the chaotic model in blue is again higher than the integral models in other colors. And here is again the plateau height, and you see this clear separation between chaos and integrability in these models.
very non-generic. I mean,
Well, yeah, this is some specific choice of block that we took. You can also take.
because in string theory, this n will be the j, and m would be the level. The most probable value of j would be, or n in your case, would be square root of m log m. So this is not very non-generic. I mean, it's what in string theory would be the first Regge trajectory in a sense. N equal m, spin equal n.
Yeah, that's possible. We picked these blocks. Yeah, I would have to think if it's feasible to do a more generic one. The basic limitation is the dimension of the block. So here, for this choice of blocks, we had dimension of the Hilbert space that was 5,000 something, so that was easily manageable. We should just make sure that we don't go extremely high. I don't know if we did runs for things that you would consider more generic, so I would have to check. If
you always took n equal m.
For the plots I will show here, yes, but for other, yeah, for the complexity things, I think we use that most of the time. Well, certainly in the things that we published, I would need to check with my collaborators whether they have other things in their desk. If there are specific values you would be interested in, let me know.
The generic value of n is square root of m log m. The most probable value.
Yeah, I don't expect big differences, but we could check. Thanks. Okay. Yeah, I probably shouldn't spend too much time on this. You can look not just at the complexity plateau height, but at the distribution of eigenvalues of this Q. And having many small eigenvalues corresponds to a bigger complexity reduction, and this could be interesting to study in itself as another measure. But let me move on to the conclusions. So we proposed this upper bound on Nielsen complexity, and we reduced it to the closest factor problem, which has been used in lattice cryptography. Important message is that our bound is able to separate integrable from chaotic systems, so I think that's very nice. The strong separation we found for SYK, where we had exponential versus polynomial Nielsen complexity, does not repeat itself for these more generic quantum resonance systems, where we always see exponential complexity. Now, the interpretation of that is not completely clear. It could be that our set of curves we minimize over just misses the ones that you need to really reduce the complexity further. So there have been some expectations, but not really backed up as far as we understand, that people think that for chaotic systems it should be exponential, for integrable it should be polynomial. If that intuition is correct, then there should be additional curves that are not well approximated in our ansatz that could push it down further. It could also be that this intuition that in integrable systems you expect power law complexity might not hold. We are not sure at this point, so that's a question for future work. So it remains to see whether possible improvements of our bound might lead to a more dramatic separation or not. I mentioned this key quantity, this Q matrix, and the fact that the small eigenvalues of Q play a role in complexity reduction. And one thing that we're currently working on is to move from the kind of systems we studied so far, which did not have a notion of spatial locality, like the localities I used had to do with the number of particles involved, but not with how far they are spatially separated. We want to move to models where we have spatial locality, and a simple class would be spin chains. And there we could see if there's additional things that happen when you play around with spatial locality in this kind of models. And for this, we also need to go beyond the assumption of non-degenerate spectra, which I briefly mentioned. But okay, we think we can deal with that. Okay, let me stop there. Thank you very much.
Okay, questions?
So just wanted to return to the sort of black hole issue at the beginning. I mean, I understand the difference between chaotic systems and integrable systems when it comes to, say, the spectra of black holes. That's sort of a nice intuitive picture of what you should. But what is complexity actually really going to tell us? If I can compute complexities of the black hole systems, what is it going to actually tell me that I need to know?
Right. So one question is how easy is it to distinguish one microstate from another? That's a question that you might be interested in. And one piece of intuition that people have proposed is that it may be very difficult to distinguish them to, say, most probes that you could use. The reason being that if the states of these black holes are highly complex, you will really need a highly non-generic operator to distinguish them. So I think from that point of view, like the question of how straightforward is it to distinguish microstates, that's one place where this complexity might play a role. And then there's others, I briefly mentioned it at the beginning, where people try to look inside horizons, etc. I don't know if you're interested in that, but there's definitely things. Okay, I can say like half a minute. So for instance, in these recent proposals that people say that you have to identify degrees of freedom inside the horizon with things in the radiation, like one of the puzzles that appears is that, well, if they're really identified as opposed to just entangled, it means that you can send signals from the radiation to the black hole, and this might seem to be acausal. Because you can choose which manipulation to do, and you can send information that way to some observer inside the black hole. And so that's a puzzle, and does it mean that causality doesn't hold? And so one proposal for that might save causality is that people have argued that the operations you would have to do to send such a signal are so complex that that the realistic observer simply does not have the time to do it. So in that sense, there is this speculation that complexity might actually underlie the causal structure of space-time, which I think is conceptually potentially interesting. Whether it's correct or not remains to be seen, of course. But there's a kind of things where it has shown up in recent discussions.
Yeah, I was just sort of, maybe you're answering the sort of follow-up I was going to make, which is, in theoretical physics, we tend to think, okay, I'll give you an infinite amount of space and an infinite amount of time to do whatever measurement you need to do to distinguish microstructure or whatever. And so whenever I hear somebody saying, well, you've got to do these very complex, subtle experiments, and it's going to take you forever, these are always questions about complexity. And I go, well, in theoretical physics, I don't care about that. All I care about is what can I measure given an infinite amount of time and an infinite amount of space.
Yeah, but that's something that people are now challenging. So
no, but I wanted to understand what that challenge was, really.
Well, so I think the claim that some people would make is that you shouldn't just think of well, okay, I'm forgetting the slogans that they use for it, but there's like high energy frontiers and there's short distances and etc. But that complexity would provide some other cutoff in the sense that if you're really focused on things you could actually measure, and often that has turned out to be essential in physics, where if certain approximations, like you can go infinitely fast or you can do this or do that, don't hold on. So the claim would be that you also need to take into account in your thought experiments the fact that you have a limited amount of time to do your measurements, and that might actually influence what you can and cannot distinguish, which I think is an interesting idea.
More questions? So maybe I have one. I mean, also in this very concrete study you have, it's clear that it's important to see how you define complexity, right? So you had a first definition and it was not good enough to make distinction, right? So is that a bit of an art, or there is, if I want to define complexity, for instance, to distinguish microstates, I mean, what is the logic on the, for instance, in your case, you have to distinguish local and non-local. Would the picture change if I don't know, reduce the number of non-local things?
Right, so I actually showed some plots where there was a dependence on the, let me pull it up again. Yeah, here, for instance, you you see if the definition of locality I use was just large enough to have the Hamiltonian local, I got these results with this small separation between integrable and chaotic. If I defined more operators to be local, then I got this bigger separation. So clearly this choice is a matter of locality degrees. There's other things. You could also ask, okay, why did I choose this cost factor mu to be equal to the dimension of the Hilbert space? So there, from what I understand, this was introduced by Nielsen to match circuit complexity quantities. So you use the geometric approach and you normalize certain things so as to match the quantities that people use in computer science. But okay, there's clearly many more possibilities, and as far as I understand, but okay, I'm quite new to this topic, so other people might know more, well, will know more about it. But as far as I understand, there's no really systematic first principles, natural definition that people would agree on. And there's actually lots of work going on in trying to see like how natural definitions can we find. So also because I was talking about operator complexity the whole time, there's this separate branch of developments using trying to define state complexity, where one looks at complexity of states as opposed to evolution operators. And also there's efforts to make the definitions as natural as possible. But okay, I don't think the last word has been said on that.
So for the microstate, the state complexity might be more relevant? Or?
I would suspect so, yes. But okay, they're closely related, but yes.
So to follow up on the same sort of point, is there any sort of universality to this notion of complexity? So let me try and put that in a down-to-earth way. Are there definitions of complexity that just see that cannot distinguish between different systems or different evolutionary processes, and then there are definitions of complexity that see huge differences between the same thing? So is there any universality that says pretty much any definition of complexity that's reasonable will say this is a very complex system and this is a very simple system, or is there just no universality whatsoever?
Yeah, I don't know. Okay, there's clearly, well, this example of bi-invariant versus with cost factors, clearly one is able to separate chaos from integrability, the other is not. So I think in this case, the conclusion people would draw is, okay, don't talk about the bi-invariant complexity. It's not good enough to distinguish clearly different types of dynamics. But I'm not sure if there's a much deeper understanding at this point. Usually, I think, okay, from the little I know in computer science, people expect that things like polynomial versus exponential times, that should be sort of generic. And if you have reasonable definitions, they should at least agree on that. But okay, I don't know enough about it to say much more than what I just said.
Okay. So if there are no more questions, we break for the coffee break, and we are back here at 11:30. Okay.
Thanks a lot.